Hello, welcome to Discrete Math, actually starting somewhat on time today. My name is Scott from the University of South Florida. This is Discrete Math Fall 2020. Yes, thank you. Reminder that next Friday is the second test. So I've already started posting stuff for the second test on to Canvas. I will have a study guide for it and various other things. But please remember, your quizzes are the thing. Now, people wanted a test review session. So last time I took a class period to do it, and as a result, we're kind of a week behind. I'm going to have to cut stuff because we're also a week behind. So that pushes one class behind. We're really kind of a week behind where the schedule is. But that's okay. I'll probably cut stuff. I might cut RSA, even though it's important, but we'll do other public key stuff. But RSA requires a lot more number theory, so we might just do enough to do Diffie-Hellman and a couple other little things. Because at the end, one thing that most discrete math classes don't do is cover regular expressions and finite state automaton, their relationship. And since regular expressions are such a big deal for IT people, I want to be able to cover them because if you're writing, doing text matching is very important. So understanding there's a bunch of tricks that you can do to work with regular expressions is like, it will make you that person that understands regular expressions in your office. And they're like, and that's important for us, right? Because we want you to be able to go every once in a while at the people working with you, especially the people who did, other majors. Are there any questions before we begin? So as I said, we'll probably cut a couple little things, and we'll cut probably one big thing, which is RSA. I'll have to look at the schedule when we get back, but there will be some cuts so we can make up to the end, make up some lost time. Okay, so today what we're going to be talking about, yes, I need to get to the quiz, and I will do a quiz review. Apparently there's some things that are still closed on the system. I will look at it and try to fix it. Let's see here. But that's class administration stuff. I will look at it after class. Okay, so we've got today's topic is we're going to introduce cryptography. We want to talk about what cryptography is, and how it works and stuff like that. And cryptography is the big thing that we want to talk about. It's one of the major application for all this number theory stuff. There are other applications as well, but the big thing is the cryptography. So that's what we're going to be talking about today, kind of an introduction to cryptography, and how the modulus thing works for that. But before we do that, we need to go over the quiz. There's a question in there whether or not I will go over the why isn't it syncing? While I see why it's not syncing, there's a question in there about will we go over it, and can I post some videos about the stuff I'm skipping? Yes, I can. Nope, there it went. Okay, well, delayed syncing. Okay, so let's talk about these things. These are all in Z5. Now, the answers are not actually -1. Okay, none of the answers here are -1 in reality or in this one. -1, because Canvas's number thing will only take numbers. It won't have, it doesn't at least I can't find an option for like D and E or does not exist. I had you write -1 in the thing, but that's not the number -1. That's just a placeholder for does not exist. You could have had you write -100 if there's no connection between -1 and does not exist, except for the fact that I had to do something to make it into Canvas. So please don't let the fact that I use -1 confuse you. All right, so 4 plus 2. So I've got Z5 here. 0, 1, 2, 3, 4. And what I've got, and notice I wanted all the answers to come back in 0, 1, 2, 3, 4. So I hope you understood those instructions. Because 6, you know, is all well and good, but it's not the answer right. 6 is not one of the options that you could choose from. You can only choose between 0, 1, 2, 3, and 4. All right. Even though 6 is an answer because 6 equals what the answer is, which is, of course, 1, right? So I'm here. If I'm here at 4, and I move 2 to the right here, I get to 1. Right? Well, 2 times 4. So if I start at 0 and I go 4 twice, 1, 2, 3, 4, 1, 2, 3, 4, I wind up at 3. Or I could think of 8, which equals 8 minus 5, which equals 3. You can do either one. Because I'd get the exact same remainder. Negative 1, I'm going to go backwards 1 from 0, and I get to 4. Now 1/2, okay? So this thing says 1 over 2 equals x, so that 2x equals 1. Now, there are a couple ways to look at this, okay? One way is to just do them all. So if I have n here, and I have 2n, this is just kind of the list method. 0, 0. And then I just add 2 on the right here. 2, 4, 6, which is the same thing as 1. 4, 1, 3, and then 5, which is 0. This is what it would look like, right? So as I move 2, I'd go from 0 to 2, 2 to 4, 6, and then when n here is, of course, 1, 2, 3, 4, and then 5, which is 0 again. So we loop back around. Now the point is here that I could do the whole chart thing. And that is a perfectly good method of doing it. I make my little chart. I reach over here. So 2 times what equals 1? 3. Okay. So I make a little chart. And I could do that. Okay. So how do we feel about that 1 to 5? Okay. Another way to do it. Well, I can also list the numbers to see if 2x is them. I could also list what 1 equals. So 1 equals, then I add 5, 6, equals, then I add another 5, I get 11, equals 16, equals yada, yada, yada. And then I look here and I go, well, 6, hey, 2 times 3. So you can just equals 21. So you can just like kind of go through it by multiplying through. Yeah, so you can think of these things in one sense like fractions, but remember, that's what a fraction actually is. Okay? A fraction is not, you know, when I get a half, 1/2 is not half a pizza. Okay? 1/2, well, even saying the words 1/2 is incorrect. This is really 1/2. Right? And it's not half a pizza. It's what times 2 equals 1. And so, yes, you can multiply this over here. You go, oh, 1 equals x times 2. And that's a perfectly good way of doing it. And that's actually kind of what you're doing. That's exactly what you're doing. So again, 1/2 is not half a pizza. It's the inverse of 2. Okay, let's look at 2/3. So 2/3 equals x, so that 2 times x equals 3. Okay. Well, we just go back to the exact same chart. Oh, I'm sorry. This is 3x equals 2. My bad. All right, 3's on the bottom. So 2/3 is the number x, so that 3 times x equals 2. Okay? So let's just do another column here. 3n. So 3n, if n is 0, 3n, and then I just add 3. 3, 6, which equals 1, 4. Add another 3, I get 7, which equals, brain, 7, 5, 2. And then I add 3 again, and I get 5, which equals 0. Okay. So if what n corresponds here to this. So here, if I want 2, I need to multiply 4. I need to multiply 4 by 2, right? Because 3 times 4 equals 12 equals, well, I could do 7, but we'll do 12 minus 5, which equals 2. How do we feel about that one, 1 to 5? Okay. I see a lot more watchers than I do voters. Go vote. Right? You know, you can't really affect the presidential election, but you can affect these because, you know, there's not many people. So, you know, a 1 vote, you know, is a major vote. You know, you emphasize. By the way, I keep getting emails from people telling me to remind my students to go vote. I'm like, one of me is like, are you sure you want me to do that? Because, you know, my students are in math, not liberal arts, but, you know, or at IT or stuff. But the other thing I keep saying, one thing that drives me nuts, when you go vote, please do vote, but when you go vote, spend a little time, this is my personal advocation, spend a little time on your vote for president actually doesn't matter very much, but your vote for your local offices, because the numbers are so small, those things matter. And remember, the magnitude by which a candidate wins matters. Okay, it matters about what that candidate can get done or not. So, or, you know, a person who wins by a very slim majority doesn't have as much power. They still have the office, but not as much power as a person who wins by a large majority. And not only that, in local elections, you can really make a difference. So actually research, you know, county commissioner, state attorney, and all these other things, district attorneys, whatever, judges, school board members, because your vote could really matter. So that's my 2 cents. And you don't have to vote for one of the big twos. You're not wasting your vote if you vote for a third party. Remember, a third party vote is a vote against them both. It's not a wasted vote because magnitudes do matter. Gore spoiling the election. I mean, not Gore. When Nader spoiled the election in 2000, the Democrats next time moved to the left. And Ross Perot, who's way before your time, did change the debate about the deficit. So it does matter. Okay, there. I've said enough. I probably already said too much to get me in trouble. So go vote. I'm told to make you go vote. Okay. Back to this. 1 minus 4 in Z15. I don't really feel like writing the whole thing out. But if I go back, that's negative 3, which equals 15 minus 3, which equals 12. How do we feel about that 1 to 5? Please, 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 please do not start doing politics. I'm sorry I mentioned it in the chat. It's my fault. I started it. Okay. 6 times 4. All right, so there are a couple of ways of doing this. As I said before, you can think of it as 24 and then subtract 15 off that, and you wind up with 9. Okay, that's one way to do it. You could do the circle with 15. It's a little bit long. And negative 1, of course, if I go 1 back, I get from 0, I get 14. All right. How do we feel about those three, 1 to 5? Okay. Yeah, so negative 1 is just 15 minus 1. I take the big clock and I go back 1. Okay. 1/2. Well, let's see. Is there a 1/2? So 1/2, I'm sorry, not 1/2, 1 over 2 is x so that 1 equals 2x. All right. So I look here. I made my little chart here. I actually made it in advance this time. Let's look at my chart. So what I'm going to do is I'm going to go down to the chart. I did, 0. I counted up by 2 here. I counted up by 3 here. Now, something very interesting happens here with these numbers. When I go through, when I count up by 2, 0, 2, 4, 6, 8, 10, 12, 14, when I get to 16, 16 is 1. Okay. So 8 will work because 8 times 2 equals 16 equals 1. How do I feel about that 1 to 5? Yeah, so you can just, if you subtract 15 and then subtract 15 and subtract 15, all of the mods are the same. Now, someone just brought a very interesting point. What is this about? Does even make any sense in Z3? Does the word even make sense? In Z15. Does it mean anything to be divisible by 2 in one sense? Well, look at this. Everything is divisible by 2. All right. I start over. Exactly. 0, 2, 4, 6, 8. But now I go to 1. So in essence, everything's divisible by 2, right? 1/2 exists. 12 over 2 exists. 10 over 2 exists. You know, everything divided by 2 exists. Now, compare that situation to the 3 situation. 0, 3, 6, 9, 12. 0, 3, 6, 9, 12. 0, 3, 6, 9, 12. There's no 1 here. How do we feel about that 1 to 5? All right. So if you want to solve these types of problems where you're looking for multiplicative inverses, the easiest way to do it is just to make a table. And that's going to be very important when we get to exponents on Monday. I want you, these tables are just so helpful because it's very easy to find answers on them if you just make the table. Okay. All right. Are there any other questions? I love this person. No vote is wasted, no matter who it's for. That's right. Go get your ballot, right? Go request your absentee ballot, get it, stuff it back into the sleeve, and just send it back, right? Register a non-vote for everything. Like, I hate them all. I despise you so much that what I'm going to do is I'm going to take the time to get the absentee ballot. I'm going to take the time to open the envelope. I am going to take the time to sign it, to stuff it back in and sign it and stick it back in the mail. To register no vote for anybody, just to make sure that I register the fact that I went in there and said none of you are worth my vote. Don't even write no, right? Just say nothing, right? There you go. Don't vote. It only encourages them, right? Yeah. Okay. So, moving on. I got to stop. Moving on. We want to introduce cryptography and ciphers today. By the way, when I said don't vote, it's one time, like 2 years ago, I was actually said in class, nobody was voting 1 to 5. And I said, well, vote, unlike the presidential elections, your vote here matter, or congressional elections. It was 2 years ago then, the last congressional cycle. People were running for governor. And I said, don't vote, you can't affect the outcome, but vote in my class. And somebody wrote, with sarcasm. And then someone wrote on my teacher instruction comments that I was discouraging people from voting. And, my boss was like, what? I said, don't ask. So, I was just like, yeah, the student could not understand sarcasm in any way, shape, or form. So, What do you want? Okay, so what we want to do is we want to talk about cryptography, which is the main application of number theory in IT, computer science, those sorts of things. So what we're going to do is we're going to talk about how cryptography works and kind of give you a historical perspective. Now, it should be noted that this historical perspective that I'm about to do is nowhere near complete. I'm skipping a lot of major people and a lot of major things. There's an excellent book. If you are interested, there's an excellent book called The Code Breakers by David Kahn. And I would love to show it to you, except I left it in my office up at school. So, oops. But it's a very good book. I highly encourage you to grab it if you're interested in this kind of historical stuff. So what we're going to talk about is cryptography. We're going to talk about why we care. We're going to talk about insecure networks. And then we're going to talk about private key systems. Next time, we're going to talk about public key systems. And we'll talk about Diffie-Hellman then. I was going to do it today. It should be noted that there is a problem set associated with this stuff. But because we are a week behind and because next week is the test, and there won't be a problem set due on test week, that problem set will be 9 now, because 8 is, of course, one of the weeks we have a test. Okay. All right. So here's the problem. Alice and Bob, and it's always Alice and Bob, by the way. I don't know why, except it's usually A and B. Alice and Bob want to transmit information over an insecure communication channel. One on which Eve, I don't know why it's always Eve. Seems a little sexist to me, but I guess Adam was taken. Because we want A, Alice, and B, Bob, so E, I guess they decided to do. One on which Eve can listen. How do they communicate? Okay. And this is basically the problem yes, there you go. Eve because of eavesdropping, probably. Thank you. So how can they communicate? And this is, an ancient problem. So the first way would be kind of a permutation cipher. These are the types of things you do as a kid, right? I take the 26 letters and I assign each another letter. But remember, when I'm doing this, I'm actually kind of assigning them a number. Let me show you how this works. So a permutation cipher. I take the 26 letters of the alphabet, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q. Wait, I'm going to do it the wrong height again, aren't I? I did this last year and it didn't come out evenly. I was sitting there waiting and then it turned out that I had two of my lines weren't right. I was about to do it again. There we go. All right, so I take my alphabet here, and I assign each one a ciphertext. So these are my plain text values, and then I assign each one a letter. So maybe I'll let this one be Z, I'll let this one be Y, I'll let this one be X here, I'll let this one be, etc., etc., etc. G here. Let's see, we'll do R here. You get the idea, right? Q. I've got, let's see, P, O, N, M, Notice here I've assigned M to itself, just, completely randomly. L. Okay. What have I got left? You get the idea. So fill in the rest for yourself, I suppose. E. What's left? I've assigned 1 twice. Nope, there it is. Okay, so I have this long message. So if I want to say go Bulls, and I'll make another one for the space. No, I can't because I would have to redo it. If I want to say go Bulls, I kind of just, look it up. So this one is K, Q, Z, P. I should have done this in advance, shouldn't I have? Note for next year. J, S. Okay, so how do we feel about that 1 to 5? I just kind of, So if Alice sends Bob a message, Alice and Bob both have a copy of the chart. Alice Alice substitutes, it's just called the substitution cipher or permutation cipher. Alice encodes plain text using the chart. Bob decrypts it using the same chart. Okay. And there are, of course, so with this type of chart, by the way, how many are there? Well, I've got 26 letters. If I have 26 letters in my alphabet, then there are 26 factorial ways to encrypt. There are 26 factorial ways to build a key. Okay, kind of a simple idea. All right. Well, but there's no public key here. This is called a private key, and it's purely private. So what has to happen? Let's look at the limitations of this system. One, it's vulnerable to cryptanalysis, right? Because what I do, right, if someone's using this type of system, what I do is I look, especially if I have a long message, go Bulls is not going to work. But if I have a long message, what I'm going to do is I'm going to look for the E's, right? I'm going to look for the most common number. That one's going to be E, the most common letter, and et cetera, et cetera. And it should be noted that these systems can get extremely sophisticated. Okay? So this is a very simple one, but this is a substitution. But what are its limitations? Right? Simple ciphers can be broken with frequency analysis. But this is not a problem that can't be overcome, okay, with this type of cipher system. Because there's one Louis the 14th. Louis the 14th's diplomatic code was a type of substitution cipher with a lot of little things in it that would first of all, he wasn't substituting the letters. He was the cipher was diplomatic team. The cipher actually encoded syllables, and it wasn't cracked until recently. So the entire syllable was then encoded as a symbol, and I don't have to use letters as my crypto text, right? I could also do something like this. I could also have go bulls, and then assign G to be the number 3. O to be the number 6, B to be the number 5, U to be the number 23, L to be the number 22, and S to be the number 16. Right? And there's no correlate, they don't have to be, so they don't have to encode into numbers. I mean, so we don't have to encode into letters. What's more, I could actually encode the blocks, right? So I could encode, instead of encoding these things, I could encode, right? I could have the sequence GOB be 3,875, and GOC equal the sequence 6,129, right? So when I put in the encoding, right, and then I could have ULL. ULL is somewhere way down on the list, and it's 2560. And then S with a blank blank is the same thing as 1,492. So I can make these extremely sophisticated. But the major limitations, so we've got, as our limitation, we've got this. Simple ciphers can be broken with frequency analysis, but I can get around that. The next major limitation is that the key is very large. Okay? So there's something, I don't know if you know this, but there's something called, you probably heard of it. It's called a book code. Okay? And the idea behind a book code is that when I encode the stuff, let's say that Algebra Chapter 0 by Paula Luffy here is my book code, right? So I'd have a message that said something like 316.5.3. Or 4.3, because there's no fifth letter. So what I would do here is I'd take, if the code, so this led to book codes. Book is secret. So, if I'm doing this by hand, I'm going to have to carry around a book. So if I had something like this, so example, let's say 316 dash 4.3 was the code. So I would go to so I would pull up my book. I go to 316, go down to the fourth line, and go to the third word. So that would be page 316, 1, 2, 3, 4, 1, 2, 3. This would be the word this. And this is a very sophisticated substitution cipher. right? I mean, it's impossible to do from frequency analysis because the more common the word is, right, the more common it's going to, the larger the numbers, the larger the number of possible codes that mean the same word, right? Because this is common. I could find another sentence with the word this in it, and that would also map to the word this. So you can get away from frequency analysis, but the problem is that your key gets huge. And that's one problem, but the real problem with that is that your key has to be secured. Your key must be transmitted and stored secretly. How do we feel about that concept, 1 to 5? This idea that what's the real limitation of this is the fact that my key is the key is huge. As the cipher, if I want to make a key that can't be broken by simple frequency analysis, it's going to get really big. Now, if I'm in an embassy with, places that respect laws of a diplomatic nature, that's not really a problem, right? I send my diplomat with the key, and this is how modern one-type pads work. I send my diplomat securely with the keys. They show up at the embassy. They go in the embassy safe, right? That's not a problem. But if you're trying to talk to soldiers on a field, it doesn't work well. Okay. All right, so that's the limit. That's the major limitation of a simple type of substitution cipher. And as I said, they can get very sophisticated. A permutation cipher. Well, to combat this, we've got something called a Caesar cipher. Or I'm supposed to say Kaiser because that's, that should be a hard C in Latin, but what the hell. A C followed by an A. If I remember correctly, my Latin is supposed to be hard. This is called the Caesar cipher. Okay. By the way, one of the things that made that Louis system so unbreakable was that some of the French pronunciations had actually changed. Modern French is not the same as the French being, just like, in English, Shakespearean English is not the same as modern English. The words, not only the words, like when Juliet says, "Wherefore art thou?" she's actually saying, "Why are you?" Right? Why are you a Romeo? It's not like she's looking for Romeo, right? It's "Wherefore art thou?" Wherefore means why. But the same things happen in French, and the pronunciations have changed. Like in English, the pronunciation of, if you look at the title of Much Ado About Nothing, that's actually Much Ado About Noting is the way that you would say. You would say that word noting in Shakespearean's time, which was a pun on noting, N-O-T-I-N-G, which, looking and spying. So there's a pun there that's been lost because the language has changed. But the same thing happened in French. And since these were syllable pronouncing, it made it very hard to crack. Okay. Well, let's talk about the Caesar cipher. The Caesar cipher idea was that I have a shift. This is just a simple cipher where what I do is I pick a number and add. Okay? So, and this is a response to Caesar needing to be able to send messages quickly. So my private key is now one number, 1 through 26 or whatever. So here's what I do. Here's what I set up. I have a chart. I do A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, Tango, Umbrella, Victor, Whiskey, X-Ray Zulu. I set it up, and then I do this. I assign these things number. I'm going to start with A as 0. That's just totally arbitrary. Caesar would have never done that because the Romans didn't have a 0. Could you imagine doing long division in Roman numerals? What's really impressive to me is that Archimedes figured out calculus using Roman numerals, or the Greek equivalent. That's what's really impressive to me. I skipped a number, didn't I? Or repeated one. All right, so did I skip a letter? Yep. Math professor not only does bad math, but he skips letters. We need to send him back to kindergarten. Okay, did I get them all? Yes, 26 letters, 0 to 25 are the numbers. Okay. So, here's how this works. My key is going to be a number. So for an example, I'm going to let my key be 1. So I want to encrypt Go Bulls. So what I do is I do the numbers associated with each one of these. So for instance, this would be a 6. This would be a 14. This right here would be a 1. This would be a 20, an 11, an 11, and a 6. All right, so how do we feel about that 1 to 5? S is 18, not 6. Okay. I can't read. Okay, so now my key, my secret key, Alice has the following key. So I'm going to do 5. So what I do for the cipher is the ciphertext equals the plain plus 5 mod 25. So my ciphertext, when I send it, traditionally ciphertext is red and plain text is blue. And also the convention is that ciphertext is in lowercase and plain text is in uppercase. So what I do is I just add 5 mod 25. So this one's going to become an 11. This one's going to become a 19. This one's going to become a 6. This one becomes a 25, which is a 0. This one becomes 16, 16. Brain, come on, brain. It's a bad day for me brain-wise, apparently. And now I just look at my chart and I go backwards. So this becomes L, T, G, oops, this should be capitals. Sorry, I forgot to turn off my phone. My big pet peeve is students with phones in class. And so I'm like, everybody turn off your phone. And invariably, I forget to turn off mine one day and it rings. L T G A Q Q X. And you can see that the 20 plus 5 equals 0. But I'm modding by 20. Oh, you're right. I'm modding by 26. I'm an idiot. Bugger. Right, because there are 26 numbers. So this should be 25. You're right. So that should be Z. And then I did a bad thing because I wanted it to be... I wanted to have one that went over and I didn't. Sorry about that. I wanted one to go over and it didn't. I should have added, my key should have been bigger than 5. Anyway, I should have chosen 10. Anyway, notes for next year. This is now my ciphertext. Now, the thing is, notice how small this key is. Okay? The key is only one character. So a person, an operator, I could give this message. So Caesar could give this message to a runner and say, run this across the, run this back to the cavalry with orders to go, run this order to the cavalry to, advance quickly on the thing. Or, attack the right flank or whatever Caesar's telling the cavalry to do. Or assassinate the runner, Rosencrantz and Guildenstern. Now, so they get that message, right? But notice that the operator now only has to remember one number. So Caesar and, Cassius, pick someone who killed him, have agreed ahead of time that 5 is going to be our key. So notice that now the person who's decrypting the message doesn't have to carry around a whole bunch of stuff. And this is incredibly insecure. There's only 26 possible keys, 25 if I throw out the one where everything's just itself. Right? There are only 25 possible keys, but I only have to remember one number. And it's very fast. A skilled operator could do this very, very quickly. It should have been mod 26 though, because there are 26 numbers. So it should have been 25, and I meant to make it, I should have made it larger. I should have made it 10, so some of these numbers wrap back around, but I didn't. Okay. If I exclude 0, but I only need to remember one number. So, and if the message doesn't have to be kept for a long time, right? If the intelligence from cracking the message would only be good for another 20 minutes, on Caesar's battlefield, he's fighting the Gauls. He'd have to, the Gaulish interceptor would, have to find someone who even read Latin. And 2, the person would have to sit there and try 26 keys. Which is enough, which may be secure enough for what you're doing. But the big advantage to it is that the key is very short. How do we feel about that 1 to 5? I only need to remember one number. Okay. All right. So that's the Caesar cipher. Okay, we'll give it a little while. People get a little bit more sophisticated with these. And two gentlemen by the name of Bastier and Vigenère. So Battista Bellasso. This guy, if you read that book on the thing, he basically, these two had a big fight because he said he published first, and this guy said he used first. What do you want? With these two guys, it's called the Vigenère cipher. Vigenère cipher, which is as good as my French is going to get. It's called the Vigenère cipher because this guy had a better publicist. But those two guys invented it. But the idea is this. The idea is that I take a longer number. Or I should say multiple numbers. So let's look at what happens to go balls. So here's my key. My key is going to be the numbers 6, 10, 5, 0. So I've got 1, 2, 3, 4 numbers. And what I'm going to do is I'm going to split my message and I'm going to use each one. So my message was Go Bulls. All right. And what I'm going to do is I'm going to split each one up into a column. So this one right here is going to be the 6 column, the 10, the 5, the 0. And then I'm going to do another 6, 10, 5. All right. My message in plain text, according to my chart up here, was 6, 14, 1, 20, 11, 11, 18. Now I add the key for that column. So in cipher, I'm going to do 6 plus 6. I'm going to get 12. I'm going to get 10 plus 14, and I get 24. I get 5 plus 1, I get a 6. I do 0 plus 20, I get 20. I do 6 plus 11, I get 17. I do 10 plus 11, I get 22. I do 5 plus 18, I get... I didn't do any that were over... Dadgummit, I still didn't do any that were over 26. Where was I? Oh, 5 plus 18, and I get 23. Now I go back to my list of things. Okay, so I've got 12 here. 12 in crypt text is M. 24 becomes Y. 6 becomes G. 20 is U again. 17 is R. 22 is W. And 23 is X. Now, notice something. So 1 to 5, how do we feel about what just happened for the encoding? Notice the L's. Which one did I do wrong? Oh, you're right. I screwed that up. '21 was V. Now, notice on this encoding here. Forgetting letters, adding ones incorrectly. One of those days. Now notice something. The first L and the second L were transmitted into different letters. What did I do? No. 21 is V. 22 is W. Okay. Now, why did I split the column? Notice what happened here. This was a repeat. So I start my message. I start by doing 6, 10, 5, 0. And then I do 6, 10, 5, 0, 6, 10, 5, 0, 6, 10, 5, 0. So if I had a really long message, for instance, if I wanted to say, go Bulls, hail, Caesar, and Caesar spelled with an A, right? Here's what I would do. I would do 6, 10, 5, 0, 6, 10, 5, 0, 6, 10, 5, 0, 6, 10, 5, 0, 6. And then when I encrypt, I'm going to add these numbers. So these are the numbers I add in each column. Okay. And what's just happened here is that I now have a 4-character key, 6, 10, 5, 0. So I have a short thing, but I have a much more secure message. Because look at these two L's. They didn't even get translated to the same letter. Now, I can do cryptanalysis on here. I can. But it's very difficult. Right? Especially for shorter messages. How do we feel about that 1 to 5? How I now have a much more secure message, but a shorter key. What's more, up here, if I wanted to do something incredibly sophisticated, the key would wind up being longer than the message that it was meant to encode. But that can't happen here. Now, here, if the key length for a visionary cipher Security is directly related to key length. As the length of the messaging, as the length of the key approaches the length of the message it is used to send, it becomes unbreakable. Okay? So if my key length is exactly the same length as the length of the message, the key becomes unbreakable. This is called a one-time pad. Now, this gets into the biggest vulnerability and security for any crypto system, and that's humans. Okay? So we need to talk about how you break these and what a crib is. The biggest vulnerability is users. The more times a key is used, the easier it is to break. Okay. And an Enigma is the, okay. The Enigma, though, is the perfect example of a bad user. All right, let's talk about Enigma. Go see the movie if you haven't, by the way, about Turing and the breaking of Enigma. It's really good. But user error and the problem of a crib. So how did Enigma get broken? If you've seen the movie, what was the thing that every German message ended that they figured out how to break the key? What was it? Right? Spoiler alert. Every message in German from the Nazis ended in what? Heil Hitler. If you end every message in Heil Hitler, you've given the people that are trying to that are trying to figure out your code, something called a crib. Now, it should be noted that Enigma is a little bit more sophisticated than just a really sophisticated Vigenère cipher. Vigenère cipher. It's more than that. It also moves things. It's got, a nice way to do the rotors and things are very, very sophisticated. It ends up being a problem in group theory, and there are problems with the way Enigma was set up. There are two major problems with the way Enigma is set up. One is the crib, and two is that the problems with the rotors turns out to be a different problem than the one with the plugs. So you can solve them independently. So Enigma gives the illusion of security without giving any more security. Okay? So if you end every message with Heil Hitler, you've given the people trying to break it a huge advantage. So the biggest vulnerability is users, and that's why we need to learn about cryptography if we're going to do cybersecurity. Okay? So let's look at the problem of a crib. Now, because the German operators did not understand what was going on, they gave everyone a crib. So let's suppose my key is 1530. A crib is a piece of plain text I know. So let's say my key is 15, 10, 5. That's enough. So 15, 10, 5 is my key. All right. And I want to encrypt the message, go Bulls. So I'm going to do 15, 10, 5, 15, 10, 5, 15, 10, 5, etc. And it's not a very sophisticated key, but okay. Now, if I want to do this quickly, if I want to encode this, I'm going to wind up, let's see, I don't feel like doing it by hand. There are websites that will do this for you, by the way. There we go. Online decoder, online encoder. So let's see, plain text, alphabet. Let's see, go Bulls. Encrypt. What was my key? My key was, so my key would be 15, 10, 5. To memorize this, I will use the letters. So I'll use P, K, F. I can also just do my keys like that. P, K, F. And let's do encrypt. For some reason, the website isn't working. This is... Okay, that didn't help. Let's try this again. There we go. So we do PK. So we do go Bulls. And we go to... there's our alphabet. Do that. And our key is PKF. All right, so I'm going to wind up with the ciphertext of VYG J V Q H. Okay, so let's just make sure we're using the same number basis. Where is it? So my number for S was 6. If I add 15 to 6, I get what? Oops. So 1, 2, 3, 4, 5, 6. I should have gotten V. Why did I get H? Let me guess, it's going backwards. Okay, I can't make this work on the site because the site is doing something I don't understand. Okay. Whatever. We'll have to do it by hand. I'm out of time already, and I have to do it by hand, and I'm not done yet. So if you want to leave right now, I understand, but you're still responsible for the material because I'm going over. Okay, 15. I want to add 15 to G. So G is 6. 14. Next year, I'll have to work out these in advance. 1. What's U? 16, 14, 1, 20, 11, 11, 18. So I wind up with ciphertext of, let's see, this one would be 21, 24, 6, 25, 21, 16, 18 and 15 mod 26. So that would be 33 minus 26 would be, yeah. And then, so this is my cipher numbers, and then my cipher text would be then be helpful if I just had the thing in front of me. VY G Z V Q H. Okay. Now, suppose I knew the end of this message was ULS. So suppose, I'm sorry, LLS. Suppose I knew the last three letters were LLS. All right, so I'm given the message V, Y, G, Z, V, Q, H. Now suppose I knew the last three letters and I know that I've got a three-piece key. So what am I going to do? I'm going to put my plain text underneath. This is what I know. I know this is L, L, L. All right, when I'm decrypting. So this is 5. Let's see, what is this one? This one is 18. So now I know that 7 maps to 18. Is that correct? I did that, right? What's more, I know that 16, I know that when I decrypt, I know that 16 will map to 11. And I know here that 21 is going to map to 10. I'm sorry, 10 is going to, yes, 21 is going to map back to 10. How do we feel about that 1 to 5? I know I'm over. Shouldn't the fourth letter be 10? Please tell me I didn't do that again. This should be 35, which is 10. Okay. Yes, you are correct. All right, but how do we feel about the fact that I now have part of the key? In fact, I have the whole key. All right. What do I do now? Yeah, so it should be 9. Sorry. Okay. Well, now I have part of the key, so now I can figure out what was done. All right. If this number here became that number there, I know that a shift took place. if this number became here, I noticed that I can either add 9, or what was done was add 15. Here, I know that the cryptography here added 5, so it's 5 this way. In order for 18 to become 7, I added 15. In order for 10 to become 21, sorry, that should be a 20, not a 21. I know I had to add 10. So now I can break it because I put a 15 here, a 5 here, and a 10 here, and a 15 again. All right, note to self for next semester, have all the examples worked out ahead of time. In charts like I did for the other thing. Do I have them right now? What should it be? Somebody figure out what it should be. Yes, I'm going to ask you to decode messages. Someone's saying that should be J. Okay, I don't know because I'm messing things up. Yes, 9 should be J. Okay. But the point is that I can now, because I have a crib, I can figure out the message. Thank you. All right. Are there any other questions about that? So, cribs, users are your major security problem. Okay? Because they'll give cribs. Any questions about that? So that's why we need to know how it works. Okay, where did I not get to? Now, the major limitation of a private key crypt system is that I have to be able to I have to be able to securely send the key. So I've already said that away. The major limitation of all of these systems. Is the key. So all private systems, these private key systems, by the way, the private key systems are still in use. AES, encryption, DES, and its subsequent AES things, these are all private key systems. So you have to transmit the key privately. And that's what's absolutely vital to these systems. So these systems are still in use. Private key is still in use. Now, they're much more sophisticated than Enigma and Visionet, right? They do something called blocks. So what they do is they take an entire block of text, and then they have a very sophisticated, they have a long string of the keys significantly long. They take an entire block of text, they flip the text around a little bit, then by some algorithm, and then they encode it. So there's a long process that goes on to this. But it's still the system, the basic idea of the system is the same. You share a private key with another person. And that sharing has to be done securely. Okay? Are there any questions about that? Okay. So that's what we did. So that's what we did today, is we talked about the basics of private key encryption and the basics of cryptography. As I said, this is just like, we wanted to get some use out of our, I know I said I'd be doing exponents. I'm going to do that next time because that's the key to how Diffie-Hellman works and public key. So next time we will do public keys, and then next year or next semester, because I am teaching next semester, this one, I will do the examples worked out in advance. Any other questions? Comments, issues, suggestions, thoughts? Hate mail. Okay, sorry for going over. Some of you sent me messages. I will look at them. Let's see. So what kind of quiz question can you get? So you can get like, I can give you like a piece of, I could give you a key and some text and ask you to encode it using a cipher. I could also give you an encoded message and a crib and ask you to decode the entire message. And part of the point is I actually don't need to know what order these things are in. I can work backwards or forwards. So again, if you end every message with Heil Hitler, your system is going to be extremely, it's going to be crackable because you've given the people trying to crack your system a crib. And of course, Alan Turing's going to build a computer and use it to crack Enigma. Any other questions? All right, then that's it. Please don't encode me saying Heil Hitler, clip me saying Heil Hitler or something like that on the thing, worse, giving a wave that looks, you clip it just right so it looks like a salute. Please don't do that. It's just wrong. Coding help. Yes, there's coding help tomorrow at 12:30. It will be, I secured the, I have that same room that I had last time. If we need more space, I can actually get a bigger room because we're supposed to be socially distancing and all that. But I made reservations for 116, so you can come in person or you can do it online, virtual. That's all fine. That's right. I'll encode the instruction. Just, click OK and submit, and you get, not going to do that. Any other questions? And again, the problem set for this material is going to be the week after the test. And don't forget, there is a test help session. It will be Wednesday of next week at 7 p.m. Anything else? Okay, that's it for me.